Okay, so hello and welcome back. So in this video I wanted to show you a simple circuit, but actually a pretty useful circuit that is something like a low-pass filter, but it's a little bit different. So let me first show you the schematic for this circuit, and then we will get to the rest of the calculation and other things related to this circuit. Okay. Okay. So basically what this circuit looks like, it's actually a simple circuit with I'll get rid of these papers. This is related to some other thing that I was doing. Okay. So basically the circuit that I have is something like is actually something like you have a basically input coming in here, some resistor, and some basically resistor over here goes to ground, and then you have a capacitor over here. This capacitor goes to ground as well, and this over here is your V of out. This over here is your V of in, and let's say that this is your R1, this is your R2, and this is your C. Okay, so I'm taking basically R1 as 1 kilo ohm, taking R2 as 1 kilo ohm, and taking C as this capacitor 0.01 microfarad. 0.01 microfarad. Okay. Now, so what's interesting about this circuit is it's pretty much like the circuits that the circuit that we had before. The circuit that we had before was basically a circuit like this, and we had the capacitor over here that it was grounded, and this was V of in, and this was V of out, and this was, as you increase the frequency here, the reactance of this resistant of this capacitor over here decreases, and then the voltage drop across that decreases, and so the voltage decreases. So it would be something like this. If this is F of in and V of out, as the frequency increases, the voltage decreases, so it's going to be something like this, and it was a low pass filter. It was a low pass filter. Okay, and let me bring you over here so that you can see what I'm doing, and then we will move up there if we need to. Okay, so that's that. Now the circuit that we have here is basically something like this. So we have this V of in, and then a resistor over here, and capacitor. And the interesting thing about this circuit is that it behaves differently for DC and AC inputs, meaning that if DC comes in, then of course DC is not going to pass through this capacitor over here. So if DC comes in, then you will have your circuit will practically function like this circuit over here. So you would have the two resistors, and R1 and R2, and the capacitor would simply not be in the circuit, meaning that because the DC your DC signal would not actually pass through your capacitor. So, and then functionally it would be a simple voltage divider circuit for a DC signal or DC voltage. If AC comes in, then of course if AC comes in, then what happens is that it kind of looks like this, for whatever reason that I don't really know, and I might actually we might actually do an experiment on that. For an AC signal, it would look something like this. So you have your voltage coming in here, and you have your resistor, and then you have your capacitor, and capacitor goes to ground. And for whatever reason, and this is going to be your V of out, and this is V of in, this is R1, and this is C. So for whatever reason, this R2 will just simply, this R2 over here will just simply not be there. We will see about that. We will see how that actually works out. Okay. So that's basically how this circuit works. Now, in order to basically test this circuit, we are going to actually use some capability of signal generators called the DC offset, which is actually an interesting thing on a signal generator. It kind of mimics what the DC offset, what it does, it kind of mimics a situation like this. So let's say that this is your oscilloscope screen, and let's say that these are the vertical and horizontal basically units on your oscilloscope screen. And if you set your, for example, your DC offset to, for example, positive 10 volts, you will have a positive 10 volt signal over here. Let's say that, for example, your volts per division is set to 5 volts per division, so then 10 volts would be right over here. So then you would have a 10 volt voltage over here, and then you can, of course, you can have a AC signal on top of this, riding on top of this DC signal, and then that would be, for example, that would look something like this. So for example, it would look something like this. Okay, so you would have an AC signal on top of this DC voltage over here. And that's basically, there are many different types of situations where you would actually have this in many different types of circuits. So for that reason, they have put that in all kinds of signal generators, and the signal generator can give you a DC voltage, and on top of that voltage some signal is riding. So then you can actually do all kinds of experiments using this kind of situation. So now what that looks like on a signal generator is actually something like this. So you have, for example, on this signal generator, I'm going to show you this because this one is the one that I'm going to use. On this signal generator, you have you have this knob over here. You have this knob that says DC offset, and then you have here you have the minimum and maximum of your DC offset that you can turn this knob and set it to minimum and maximum. And then there is off, positive, and negative. And positive is going to give you a positive DC offset, negative is going to give you a negative DC offset. I'm going to show you on an oscilloscope what that means, and that's basically all there is to DC offset. Of course, I'm going to show you what that actually is. So if I connect the, where is that thing? Okay. So if I connect the output of this signal generator to the oscilloscope that I have, which is basically, let's connect this over here to channel 1. Okay, and then that is now the output of the signal generator on channel 1. And I need to bring you over here so you can see what's going on. Okay, so as you can see over here, this is the output of the signal output of the signal generator, which is basically, now this is the channel 1 is set to 5 volts per division, so this is 10 volts peak to peak and 10 volts peak to peak on AC, and it is basically, and the frequency of this signal is actually, as you can see over here, it's 1.9 horizontal units for a complete cycle. 1.9 horizontal units for a complete cycle. 1.9 times 50 microseconds. So if I multiply 1.9 units times 50 microseconds, so that's 10 raised to the power -6. That's 19 by 200,000, and if I take the reciprocal of that, I will get basically 10.5 kilohertz. 10.5 kilohertz, and that's basically my signal, the frequency of here, 10.327 kilohertz. So that is basically the signal that I have. Now if I go up here and set the DC offset to positive, okay, and play with this knob, I'll see what happens over here. You see, it seems that nothing is happening, right? And that's because the oscilloscope is set to AC. So once you're set to AC, you're not going to see DC actually. So if I set this to DC and then play with that knob up there, what I'm going to see is, you see that your signal is actually moving up. Okay, your signal is moving up. Now this was positive. This was actually positive. This was actually positive offset. You see, this is positive offset, and this is positive. because this line over here, if I ground this, you see this ground line, this is actually the line, the zero or the reference line for this signal. And then if I go to AC, you see that the signal is centered around that line, or centered about that line. And if I go to DC, it's still centered about that line. Now if I play with that knob over here, you see that I go above that center line and I can come back there. So that's basically now I have a positive offset of, for example, 10 volts, because this is 5 volts, and this is, now the line has moved over here, and now this signal is centered about this line over here, which is in the center of the signal. So that's 2 vertical units, 2 times 5 is equal to 10. So now my DC offset is positive 10 volts DC actually. And if I move the DC offset to negative, I will get a negative. Now it's off, and negative, you see, I move down here. That means that now the DC offset has a negative 10 volts. So that's basically your DC offset. And if you want to actually measure this DC offset on for example, a multimeter, you can do that. And how you can do that is basically, I can disconnect this thing from here. And disconnect the output of the signal generator from here, and then what I can do, I can connect the output of the signal generator to this cable, and now this cable is giving me these 2 clips, and now I have this multimeter. I set it to volts DC and connect the output of the signal generator to the probe of my multimeter, and volts DC, and now you can see that it is at 9.8 volts, 9.86 volts DC. But on this multimeter, if you don't have if you don't have a positive sign over here, that means that you have connected your leads in reverse polarity, meaning that you have connected positive to negative and negative to positive, which is actually not the case. I have connected positive to positive and negative to negative, but it's still showing me some negative voltage. And what that means is that basically the DC offset here is set to negative. That means that I have a negative DC offset. If I set to positive, now you can see that the positive sign is over here. That means that now the signal is above that line, not below that line. So that's basically my signal. And while we are here, I can also show you the signal itself, and the signal itself was 10 volts peak to peak, as you remember. So if I go to AC, and basically you can see that you can read 3.48 volts peak to peak. I'm sorry, 3.48 volts, and this is an RMS voltage. So 3.5 volts, let's take that as 3.5 volts. And there are 2 formulas that you need to actually remember, which are actually very important here. So one of them is basically if you have a peak-to-peak voltage, and you want to, from that peak-to-peak voltage, you want to get the RMS voltage, you have to multiply your peak-to-peak voltage by 1 over 2 square root of 2. That means that V of RMS is equal to 1 over 2 square root of 2 times V of peak-to-peak. And if you have V of RMS and you want to, if you have V of RMS and you want to get peak-to-peak voltage, you have to multiply your RMS voltage by 2 square root of 2. Okay, so V of peak-to-peak would then be equal to 2 square root of 2 times V of RMS. Now, the RMS voltage that I read over here was 3.5 volts. So V of RMS was equal to 3.5 volts. So if I put this in this relationship, which is then V of peak to peak would be equal to 2 square root of 2 times 3.5. 2 square root of 2 times 3.5, which is equal to 7 square root of 2, which is equal to 9.9 volts, meaning 9.9 volts peak to peak. And that's basically how you can read the offset voltage and how you can read the peak to peak voltage on a multimeter. Of course, for that, as you saw, you need an RMS multimeter, and on your RMS multimeter you would read the RMS voltage, then you would have to convert it to peak voltage or peak to peak voltage depending on your requirements. So that's basically that. Now let's get to that circuit and let's see what we have in the circuit. So the circuit that we had was basically this circuit over here. It's actually interesting, very interesting circuit. So the circuit is actually something like this. Now forget about these two for now. We will just focus on this one. And the voltage, the circuit that I have is you have a 1 kilo ohm resistor over here, 1 kilo ohm resistor over here, and a capacitor that is about 0.01 microfarad. Now I want to actually, it's not very important about the tolerance of the capacitor or the resistors that we have. So let's not worry about that. So to build this circuit, I have these two basically 1 kilo ohm resistors, and I have this capacitor, and this is the positive and negative rail input voltage over here. So as you can see, the input voltage goes through a 1 kilo ohm resistor and then is connected to these two components, and these two components go to ground. So I connect this to the positive rail. Connect this to the positive rail this way. Okay, and then this resistor, for example, will be connected to the other end of the other resistor and going to ground. And then also this capacitor will be connected to the same and then going to ground. So that's basically the whole circuit here, these three components. And now if I connect a signal generator to this circuit here, oops, I actually had the right thing in here. If I connect this signal generator here, Okay, so now I have the signal generator. I have the positive to positive and negative to negative. Okay, so what happens is that I'm going to need an oscilloscope in order to see what's going on in this circuit. So I connect my oscilloscope probes over here, and then this is channel 1. So channel 1 I connected to the input. So this is the ground, and this is the input, and channel 2 I connected to the output. So this is again the ground, and this is the output. Okay, so now if you go to let's take a look at the oscilloscope. Let's see what's going on in there. Sorry about this camera. Okay, so now if we take a look at the oscilloscope, what we will see is that so what you see on this oscilloscope is that this is basically channel 1, and there's an DC offset on there, and the DC offset is about 10 volts. So I make the DC offset exactly 10 volts. Okay, and you know the DC offset is 10 volts because see, when I ground channel 1 and I position this exactly on this center line over here, okay, if there was no offset here, and if I went to AC, you see this signal is 10 volts peak to peak, and you know that because this is 5 volts, basically 5 volts per division, so 2 divisions, that's 10 volts peak to peak, and this 10 volts peak to peak is centered exactly around or about this horizontal line, which is this horizontal line over here. Okay, now if the horizontal line or the ground line or the reference line is over here, if I give this signal 10 volts, positive 10 volts offset, this signal should go up here and it should be centered around this line over here. Okay, so now if I give this signal at 10 volts DC offset, positive 10 volts, so you saw as I turned on the offset, something happened over here, and then the signal came back to where it was. And the reason for that is that the oscilloscope on channel 1 is set to AC. When you're on AC, you're not seeing any DC. The DC is basically blocked off. So if I went to DC, then now you can see that your signal has jumped up here, and now it's centered about this line, which is 10 volts above the reference line that we had. So that means that the offset voltage is actually 10 volts. And whenever you're in doubt, you can just simply take a DC multimeter and just basically measure the voltage that is coming in, the DC voltage that is coming in on this channel. So that's basically what you can do. So now I know what's going on with my signal over here, and with channel 2, if I set this to dual, now you see that the channel 2 is over here, and it's set to basically it's actually about 2.5 volts output. I'm sorry, 5.55 volts output. So now, of course, you know that this is a filter, and when but you see it's actually basically what happens is, if I ground this signal over here and move that right over here, and I need to actually some adjustment over here. Whenever if you take a look at this, horizontal line, it's not exactly horizontal. This end it's a little bit tilted, so you can use the trace rotation here in order to rotate this thing. You see, as I'm rotating this thing, the whole thing is rotating. So you need to rotate this, rotate it until it's completely right. Okay. So now, if now this channel B, which is basically this channel over here, is grounded, right? Is on ground. So you're not seeing anything. That means that this line is actually the ground level for channel B. Now, if I go to AC, you see your signal over here exactly around that ground line. Okay, but if I go to DC, you see that the signal jumped up a little bit, and the signal jumped up because there is some DC offset on it, and the DC offset is on this signal is actually coming from the DC signal is actually coming from your input, and of course your output is the same thing as your input, but going through those basically the resistor and the capacitor and so on and so forth. So the same offset that you have on your input, you have it on your output as well, but it might actually be different a little bit. And you see that the offset that we had on the input was actually 10 volts DC. But the ground that we have here is actually from this line over here all the way up to this line. That means that one division on channel 2 and one division on channel 2 is 5 volts. That means that the amount of DC offset over here is only 5 volts, not 10 volts over here. Okay, so now and the output itself, of course, is as you can see is basically one vertical unit, which is 5 volts, so 5 volts peak to peak, but here your input is 10 volts peak to peak. So that means that your input is 10 volts peak to peak AC, and your output has become 5 volts peak to peak AC, and then on your input you have 10 volts positive 10 volts DC offset, on your output you have 5 volts DC offset. So that's basically what happens to your signal through this circuit. And of course, if you now I'm going to basically make a little bit of a change to my signal. So now I'm on 1 kilohertz. Okay, now I'm on 1 kilohertz on this and the voltage, and now I'm on 280 around 105 hertz, and you can see that the voltage is about 5 volts. If I go down to 11 hertz, if I go down to about 11 Hertz, which is not very easy to see anymore because I cannot actually trigger on it anymore. Okay, so at about 11 Hertz, the output is still about 5 volts, but here the output is still about 10 volts, right? Now if I increase the frequency, if I increase the frequency by a factor of 10, the output amplitude did not change yet. And if another factor of 10, it still did not change much. Another factor of 10, it did not change much. It's still at about 5 volts peak to peak. Another factor of 10, 100 kilohertz. So now the output is about, you see over here, is about less than 2 volts. So now the output is changing. Okay, so that's basically what's happening to your output, and that's basically it. Now there is a whole bunch of calculation that we can do with this circuit as well. So now what I'm going to do is that I'm going to basically we are going to monitor the input voltage and output voltage for a few different frequencies. For example, we will start at something about 60 Hertz or something like that, and we'll go all the way up to around 500 kilohertz or so, and then we will take a look at the output voltage and the DC offset on the output and see what happens there, and then we will get to the calculations related to the circuit, see what, because this circuit is actually, it's a little bit tricky to calculate what happens there. So but it's an interesting thing. I mean, it's an interesting option if you want to have basically one single filter and then send either AC or DC at different times into the circuit, and then depending on whether you're sending in AC or DC, then your output is going to, the circuit is basically going to behave differently for different inputs. So then we are going to basically jot down some values for some different frequencies, and then we will do some calculations on this circuit. But before that, let me take a few minutes to rest, and then I will back with you with the rest of this. Okay, so now in order to jot down some values for this circuit, I'm going to start at a very low frequency, and you know that this circuit is actually kind of like a low pass filter, meaning that at very low frequencies it's going to give you a high voltage, and then the voltage is going to rise down and come down, and the curve is going to be something like this. If this was frequency, if this was voltage, then the curve would be something like this. So for very low frequencies, we are going to have a fairly large output voltage, and then as we increase the frequency, as you saw, the voltage is coming down. So and one more interesting thing that you have in this circuit is that of course for a DC power supply, it's going to basically act exactly like a simple voltage divider, as I showed you in the beginning of the video. Meaning that if I for example set this power supply to, for example, 15 volts, if I set this power supply to 15 volts and connected the power supply to the circuit, so you see I disconnect this thing from here. I disconnect this thing from here, the signal generator. I disconnect it and connect a simple DC power supply to this circuit. So what's going to happen is that is going to give me an output voltage of, the output voltage is going to be, so if this is your ground, so this is channel, what you can see is jumping up and down is your input, and so it's 3 vertical. It's hard to see actually over here, even I can't see. So 3 times 5 is equal to 15 volts, which is basically the voltage that I have set in on the power supply, and the output voltage over here is right over here. If I bring it down on this line, and now it's set to 2 volts peaks, 2 volts per division. So if I go to AC, I see nothing. DC, I see basically 1, 2. So it's 1, 2, 3, 3 point, let's say about 3.8 vertical units. So 3.8 times 2 volts per division is going to give me 7.6 volts, which is half of the supply voltage over there. So this is 15 volts, this is 7.6 volts, and that's because of those two 1 kilo ohm resistors in series. So it's giving me half of my input voltage. So that's basically one more thing. And then now I'm going to connect the signal generator back, and let's do a couple of readings here, and then we will go to calculation. Okay, so I'm going to, so what I'm going to do here now is start at, let me just prepare a simple table here for frequency, F of in and V of out, for example. So I set the frequency to about 50 hertz, or about 40-50 hertz. Okay, so as you can see, I can see actually nothing. At about 50 hertz I can see nothing. Oh, I have to slow down the oscilloscope a little bit. And I can actually even trigger on that, which is interesting. Okay, so as you can see, of course on the camera it's not very interesting right now, but as you can see, I'm right now at 40 hertz. At 40 hertz, this is my output voltage. And it's on the DC offset, and let's see. So this is my input voltage, and this is at basically 10 volts peak to peak. 10 volts peak to peak, and the DC offset is 10 volts and 10 volts peak to peak, right? So about this output, the baseline is over here, and it's about, so if I go down here, if I go down here all the way to, so your signal is from basically from, the signal goes from here to somewhere over here. So if I bring this signal down, it's right over here. So it's 2.6 units. 2.6 units, right? So it's 2.6 units times 2 times 2 volts, which is equal to 5.2 volts. Which is 5.2 volts peak to peak. 5.2 volts peak to peak. And the offset voltage for the output, the offset voltage for the output is actually right over here. So it's actually between these. So 1, 2, 3, 4, 5. So it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 6.5 would be 1, 2, 3, 4, 5, 6. 6.5 would be over here. So that's right over here. And it's 2.5 units. 2.5 times 2. 2.5 times 2 is equal to 5 volts peak to peak. I'm sorry, 5 volts DC. 5 volts DC. Okay. And your the frequency is 40 hertz. 45 hertz. Okay. Now, so now let's take a look at the, let's bring up the frequency a little bit. So by a factor of 10, for example, and the DC offset of this didn't change, and the DC offset of this one didn't change, and the amplitude of these two did not actually change. So it's still at around 400 hertz. The DC offset over here, as you can see, if you go halfway between these two, you would get basically 1, 2, 3, 4. So it's 0.8 and 1.8 and 2. So it's 2.6. The amplitude of this is 2.6, basically vertical units. 2.6 times 2, which is basically the voltage over here, is still 5.2 volts. So the voltage did not change, and the DC offset did not change. So at 398 hertz, the same values, 5 volt and 5.2 volts peak to peak. Now I increased the voltage by a factor of 10, meaning that from 400 hertz I go to around 3,966, around 4,000 kilohertz. I'm sorry, 4,000 hertz or 4 kilohertz. And as you can see, nothing really changes as far as the DC offset and the amplitude of these two signals are concerned. Nothing really changes except for the frequency. So that's basically for that. That's basically about that. And so at 3.967 kilohertz, I'm still having the same values for the signal. except for that again the frequency has changed. So now if I increase the frequency by another factor of 10, now you see that the amplitude is changing. So I go down here to about, for example, 10 kilohertz, right? At 10 kilohertz, as you can see, this signal, the input signal down here, up here, is basically 10 volts peak to peak. This signal over here is about basically the same value, so it's 0.8, and it's basically 1.8, so 2.4, 2.6, the same value, and the DC offset is again the same value. So at 10 kilohertz, you have the same value. Now I increase the frequency a little bit, and you can see that the frequency, as I increase the frequency, now the amplitude of this thing is actually changing. You see over here, as I increase the frequency, the amplitude of this signal is changing. So for example, at 30 kilohertz, now this signal over here, is at basically 10 volts peak to peak, and the DC offset has not changed. This is the source or the input, and the output is at so your baseline is over down here, and your now the DC offset is basically this value. So this is 1.4, let's take it as 1.5, and 0.7, 0.9, 1.9. So 1.9 divided by 2 would be 1.9 divided by 2 would be 0.95. So if you go up 0.95, you would get to the new baseline, which is basically your DC offset. So it would be half of the distance between these two. So you have 1, 2, 3, 4, 5, 6, 7, 8. So you go 1, 2, 3, 4, and then half of this. So you would be half of this distance over here. So that is 1, 2, 2. So that's 2.2, 2.4, 2.5. So 2.5 times 2 is equal to, the offset is still at 5 volts. The offset did not change. But your output voltage is now at again, if you measure this thing, is at basically one complete unit, 1.2, 1.4, 1.6, and 1.7. So 1.7 times 2 is equal to 3.4 volts. 3.4 volts peak to peak. Okay. Now if I go to, for example, if I move to, I don't know, 60 kilohertz, 60.8, if I move to 60 kilohertz, still that offset most probably did not change. So I have the same signal over here. You see the signal is still there, and the offset for that is 10 volts, and the offset over here is at 2, 4, 6, 8, 10 and 12, so 0.6 would be right over here, so right between these, I mean the exactly between the two peaks of this signal. And the baseline over here is this thing, is this line over here, so 1, 2 and 1.2, 1.4, 1.5, sorry, 2.5. So 2.5 times 2 is 5 volts, so the offset is not changing, right? So your offset is not changing, and the frequency is 60.224 kilohertz. 60.224 kilohertz. But the voltage over here now is about 1.2 times 2 is equal to 2.4 volts peak to peak. Okay, so now if I go to, for example, I don't know, 90 kilohertz, 90 kilohertz. You see again the DC offset of your output did not change. It's still at basically halfway between these two peaks. So that would be basically that's 1, 2, 3, 4 units over here. So right over here. So right over here is your DC out, is your DC offset. It has not changed. But the amplitude of this signal is now 0.8 times 2, 0.8 times 2, which is equal to 1.6 volts. 1.6 volts peak to peak. 5 volts basically offset, and then that's at 90.90 kilohertz. Now if I move to 100, for example, 20 kilohertz, you see that now the DC offset is actually changing a little bit, meaning that you see your baseline for the DC offset is over here, and now it's moved to basically 1, 2, 3, 4, and 5, so it's right over here. So 0.6, that's like 2.6. So 2.6 times 2 is equal to 5.2 volts. So the DC offset actually changes a little bit, but not that much really. And I'm at 120.255 kilohertz. 120.255 kilohertz, and the voltage over here is at let me turn off channel 1. Sorry, turn off channel 1. DC. So this is channel 2 actually. I cannot. Okay, so if I turn off channel 1, I cannot. I would not be able to. This is as much as I can go. Okay, so I suppose you cannot see anything right now. Focus intensity, so I cannot do much anymore. But at 120 kilohertz, this is my signal over here. I cannot see it really. So let's so it seems that, well, you see over here the problem is that now this is my input and this is my output, but now the input is actually moving out of the screen because I have to turn up the sensitivity over here in order to see something over here. But that's not the problem. I mean, right now right now I'm over here. I mean, and that's the difference between a good oscilloscope and something, I mean, very entry level oscilloscope. That, for example, a good oscilloscope would have a DC offset on over here as well, and then you would be able to actually set some DC offset for your signal and then move them down here without losing the much information about your signal here. But that's basically all that we can do right now. So so again, this is my output up here, and now my output over here is right down here, but you cannot see it. But now you see that it's it's 1, 2, 3, 4, 5, 6, and 7. So 3.5, 1, 2, 3, 3.5 right here. So you have 1, 2, 3, 4, 5, 5.1. So 5.1 times 1, 5.1 times 1 is your offset, which is equal to actually 5.1. 5.1 at 120 kilohertz, and the amplitude of this voltage is actually 1, 2, 3, 4, 5, 6, and 7. 7 times 1 is equal to 0.7, actually 0.2, 2, 4, 6, 8, 10. 2, 4, 6, 8, 10, 12, 14. 1.4 times 1 is equal to 1.4 volts. 1.4 volts peak to peak. And then I can increase the signal, the frequency a little bit more still. So I can go to, for example, I don't know, 120, around 300 kilohertz. And then you would, at 300 kilohertz, I would be right over here, but then I wouldn't see anything actually. Okay, so that's all that I can do really here. Now let's move to this oscilloscope. Although I don't really trust this oscilloscope anymore, but let's see what we can do here. Okay, so now on this oscilloscope, if I go Alt, Auto, A, and I want to see DC, I want to see DC here. And where are my channels over here? No, this is not working properly. This is not working properly. Okay. Actually, I'm not seeing anything here. Okay. I'm not seeing anything here. No. No. All right. Okay, so that's basically the extent of. I mean, more than that, I cannot actually drive these oscilloscope unless we get a better oscilloscope probably. But I guess that's enough for basically the data that we have is actually more than enough, so we don't have to worry about the rest of this thing. So now in the next video, what I'm going to do is that I'm going to actually do some calculations here, and we will go through some calculations together and see basically how you could actually calculate these output values for such a circuit. So I'll see you in the next video. Thank you.